A colossal stone block weighs more than a dozen elephants. Ancient civilizations across the globe moved and shaped these giants with a precision that still baffles our best engineers today. This is the enigma of ancient quarry systems, a worldwide phenomenon pointing to a sophisticated, lost stage of human technology. By the end of this exploration, you will see these stone marvels not as silent ruins, but as loud clues to a forgotten chapter in our history. How did workers in Egypt cut granite with stunning accuracy using what we believe were simple copper tools? What forgotten methods allowed the movement of a 1,000-ton stone in Lebanon? What does this say about the true timeline of human innovation? Are we ready to question the story we have always been told about our past? This shared understanding of stone is etched into the earth from one hemisphere to the other. In Egypt, the granite quarries of Aswan present a landscape of intentional giants. Here lies the famous unfinished obelisk, a colossal shaft that would have been the largest ever erected, had a hidden crack not forced its abandonment. It remains partially attached to the living bedrock, a frozen moment in time that shows us the exact methods of extraction. Workers carved deep trenches around the obelisk, prying out the stone not with brute force, but with a meticulous process of pounding with dolerite balls and inserting wooden wedges that were soaked with water to expand and fracture the granite along precise lines. This was not guesswork, it was a masterful application of geological knowledge. Half a world away, at the high-altitude site of Puma, Punku in Bolivia, the story repeats with a different stone but a familiar, bewildering precision. The quarries for the andesite used here are located many miles away across challenging terrain. The stone blocks themselves are not rough-hewn, but are instead characterized by their complex, interlocking geometric cuts, razor-sharp edges, and perfectly flat surfaces that seem to have been machined. The sheer uniformity of these techniques, appearing in cultures separated by vast oceans and millennia, is what captures the attention of researchers. Geologist Robert Schoch, among others, has noted the operational similarities. He suggests that the scale and the specific methods point toward something more than isolated, parallel development. It hints at a coordinated, perhaps even a global, technological tradition. When you see the same sophisticated approach to quarrying in Egypt, in Bolivia, in Lebanon, and in Peru, the old narrative of completely isolated civilizations inventing the same complex methods by pure chance begins to fray. This widespread evidence forces a profound reconsideration. Were these ancient cultures connected in ways we are only beginning to grasp? Did a wave of knowledge sweep across the ancient world, leaving behind these stone fingerprints? Or does this point to a common, much older source, a lost wellspring of engineering prowess that various later cultures drew from and attempted to replicate? The quarries are not just pits in the ground, they are open books, and we are only now learning how to read their most startling chapters. The unfinished obelisk in Aswan offers a clear window into this ancient mystery. Lying in its granite bed, the colossal block is surrounded by trenches cut with an almost unnatural straightness. The sides are incredibly smooth, the corners perfectly sharp. According to mainstream archaeology, the primary tools available were stone hammers and soft copper chisels. Yet anyone who has worked with granite knows that copper is too soft to make a significant scratch on such a hard stone, and pounding with dolerite hammers would typically leave a rough, fractured surface. So how did they achieve such flawless, almost polished cuts? The discrepancy is undeniable. Modern experiments consistently fail to replicate this precision using only the tools we attribute to the Egyptians. The results are always rougher, less controlled, and far more time-consuming. This gap between accepted history and physical evidence fuels compelling theories. Perhaps they employed advanced abrasive slurries made from crushed quartz or other hard minerals, creating a primitive but highly effective sawing action. More speculative ideas propose the use of sonic or vibrational tools that could have resonated with the stone, allowing it to be shaped with surprising ease. This same precision is mirrored high in the Andes of Peru at Ollantaytambo. There, massive andesite blocks feature similar flawless seams and intricate, interlocking cuts that would challenge modern diamond-tipped tools. The technological refinement on display in both Egypt and Peru simply does not fit neatly into our linear timeline of human progress. It points to a sophisticated understanding of stonework, a knowledge of materials and techniques that seems to have vanished, leaving behind only these magnificent stone puzzles. What specific tools or processes are absent from our historical records that could explain such masterful work? The challenge of cutting these stones pales before the puzzle of moving them. Across the world, ancient builders transported blocks of a scale that would make even today's engineers pause. Consider the stone of the pregnant woman in Baalbek, Lebanon. This single block of limestone weighs an estimated 1,000 tons. That is heavier than 3 fully loaded jumbo jets. Its journey from the quarry to the temple complex spanned miles of uneven ground. Modern heavy haulers with hydraulic systems would struggle with such a load, yet the evidence tells us our ancestors accomplished it. How? The classic explanations involve armies of workers using wooden sledges, rollers, and ropes. While these methods work for smaller stones, applying them to a 1,000-ton megalith introduces staggering logistical problems. The ground pressure would crush any wooden sledge or roller into splinters. The sheer number of people needed to pull it would be impossible to coordinate. Experimental archaeology has tried to replicate these feats, yet the results are often inconclusive or require ideal conditions that rarely exist in the real world. This gap in understanding has led modern engineers to propose more sophisticated solutions. Perhaps they used a system of counterweights and pivots, a kind of ancient walking mechanism that could inch the block forward with minimal friction. Maybe they employed advanced leverage, using the landscape itself as a fulcrum to redistribute the immense weight. These are not just clever ideas, they are necessary to explain the physical reality. This implies a profound, almost intuitive grasp of physics and mechanics, a knowledge of force and balance that seems out of place in our conventional timelines. The movement of the Baalbek stones is not an isolated marvel. It is part of a global pattern of transport that defies simple explanation. This shared ingenuity points toward a deeper, more unified understanding of the material world, a forgotten science of moving mountains that we are only just beginning to decipher. The sheer ambition of these projects becomes even more staggering when we see where they chose to build. The most challenging quarries are often found in the most inaccessible places on Earth. High in the Peruvian Andes, at sites like Ollantaytambo, builders sourced gigantic andesite blocks from mountainsides thousands of feet above the valley floor. The effort to extract, shape, and then lower these multi-ton stones down near vertical cliffs would be a formidable task even with modern machinery. It suggests a level of planning and confidence that goes far beyond mere necessity. This pattern repeats on the remote expanse of Easter Island. At the quarry of Rono-Roroku, a volcanic crater, the famous Moai statues were carved directly from the crater's wall. Hundreds of these giants, some weighing over 80 tons, were then somehow moved miles across the island's rugged landscape to their final ceremonial platforms. The conventional explanation of log rollers and large teams of people faces serious practical hurdles. The island's limited resources, particularly its tree cover, make the logistics of such an operation difficult to sustain. This forces a deeper question. What powerful motivation could compel a society to undertake such a back-breaking, generation-spanning project in such an isolated location? Was it purely spiritual devotion, a drive to honor their ancestors that knew no physical limit, or does the location itself hint at a forgotten practicality? Some researchers propose that the builders possessed a sophisticated understanding of their environment, perhaps using the natural contours of the land in ways we have not yet deciphered. They might have employed a rocking, walking motion to maneuver the statues, a technique that would require less raw material than building extensive ramps. The incredible effort invested in these remote sites implies a social structure of immense coordination and a shared purpose that unified the entire community. This points to something more than a simple tribal society. It suggests a civilization with a powerful, centralizing vision and the technological ingenuity to make that vision a reality, no matter the obstacle. The stones in these far-flung quarries are not just monuments, they are testaments to a human will so determined it challenges our very understanding of what ancient people were capable of achieving. This deep understanding of stone extended far beyond simple extraction. Ancient builders were not just moving rock, they were master geologists in their own right. They possessed an almost intuitive knowledge of the Earth's materials, selecting specific types of stone for their unique properties. In Egypt, they chose granite from Aswan for its incredible hardness and enduring beauty, ideal for monuments meant to last for eternity. In Mesoamerica, the Olmecs and Maya sought out dense basalt to carve their colossal heads and intricate stelae, a stone capable of holding fine detail against the ravages of a tropical climate. This was not a random selection process. It was a deliberate choice based on a profound understanding of material science. Their expertise did not stop at selection. When you stand in an ancient quarry, you can see how they read the landscape like a map. They identified natural fracture lines in the bedrock, weaknesses formed over millennia, and they used these to their advantage. By channeling their work along these pre-existing planes, they could split gigantic blocks from the earth with a fraction of the effort it would otherwise require. It was a brilliant application of working with nature rather than against it. Geologists who study these sites point to another telling detail: the consistent avoidance of flawed stone. The quarries are littered with partially worked blocks that were abandoned the moment a hidden crack or a crystalline imperfection was discovered. This indicates a sophisticated grasp of structural integrity. They knew that a single flaw could compromise an entire monument, and they would not waste their immense labor on inferior material. Where did this flawless, almost academic knowledge come from? Such expertise implies a long tradition of trial and error, a cumulative knowledge built over countless generations. Yet, the precision we see in the earliest known quarries is already remarkably high. This presents a fascinating possibility. Could this mastery be an inherited knowledge, a technological package passed down from a much older, more advanced culture that had already perfected the science of stonework long before the rise of the empires we know from the history books? The stones themselves seem to whisper that we are missing a foundational chapter in the story of human innovation, but the quarries hold another, quieter mystery. Walk through the vast limestone quarries at Giza, the very source of the Great Pyramid's 2 million blocks, and you will find something profoundly telling in its absence. Where are the tools? The sheer volume of stone worked here should have left behind a veritable industrial graveyard of broken implements, mountains of metal shavings, and worn-out drill bits. Yet the physical evidence for the copper chisels and saws we are told were used is startlingly scarce. This is not a problem unique to Egypt. At countless ancient sites, the expected debris from large-scale stoneworking is simply missing from the archaeological record. If they were using soft copper tools to cut hard limestone and granite, those tools would have blunted, shattered, and been discarded in staggering quantities. So where is the evidence of this industrial consumption? The silence of the quarries speaks volumes, forcing us to consider that the real tools might have been something entirely different, something that left little to no trace behind. Some researchers point to the possibility of stone-on-stone percussion, using harder rocks like dolerite to pound and abrade the stone into shape. This could explain the lack of metal residue, but it struggles to account for the flawless, polished finishes and the intricate, internal cuts we see. Other, more speculative theories propose the use of organic chemical agents, plant-based solutions that could have temporarily softened the stone, making it pliable like clay for a short time before it rehardened. While intriguing, direct evidence for such a process remains elusive. This persistent gap fuels a compelling line of thought. Perhaps the tools were not simple chisels and hammers at all, but something more advanced. What if they used sophisticated alloys, a lost metallurgy that created blades far harder and more durable than basic copper, tools so valuable they were meticulously collected and recycled, leaving nothing behind to find? Or could the method have been energy-based, employing focused sound waves or even some form of concentrated heat to fracture and shape the stone through vibration and resonance? A technology that would leave no physical tool behind, only the perfectly cut stone itself. The absence in the quarries is not an empty void. It is a space filled with questions, pushing us to look beyond the conventional toolbox and consider the possibility that an entire branch of ancient technology, a science of shaping stone, has vanished without a trace, leaving only its magnificent, silent results for us to ponder. This uniformity in stonework appears too consistent to be mere coincidence. Walk from the tightly fitted walls of an Inca fortress in Peru to the colossal granite blocks of an Egyptian temple, and you will notice a recurring theme. The stones, though from different continents and quarried from different types of rock, often share a startlingly similar approach to their design. They are frequently cut to standardized sizes, with edges that interlock with their neighbors in perfect, seamless joints. This is not the result of random chance or rough approximation. It is the hallmark of a master blueprint, a system built on precise measurement and repeatable processes. Imagine trying to assemble a vast, three-dimensional puzzle where every piece weighs several tons. Without a universal standard, without a shared language of measurement, the entire structure would be chaos. Yet, these ancient builders achieved a level of consistency that speaks of a highly organized and deeply sophisticated engineering culture. How could cultures separated by oceans and thousands of years arrive at such a similar, complex solution? Researchers like Graham Hancock observe that this widespread consistency is difficult to explain through isolated development alone. He and others suggest it points toward a common ancestral knowledge base, a foundational school of thought regarding stone construction that various cultures inherited, adapted, and expressed in their own unique ways. The ability to produce these standardized blocks on a massive scale reveals something crucial. It was not just about one team of skilled artisans working on a single project. It indicates an entire technological framework, a system that allowed for the training of workers, the replication of designs, and the guarantee of quality control across generations. This implies the existence of something we take for granted in our modern world: precise measuring tools and physical templates. They must have used standardized rods, angles, and perhaps even early forms of gauges to ensure that every block, whether it was the first or the 1,000th, would fit perfectly into the grand design. The stones themselves are the silent testimony to this lost system of mass production. They hint at a forgotten industrial standard, a set of rules and techniques so effective that its echo can be seen in the greatest stone monuments around the globe. This shared architectural language challenges the idea of these civilizations as entirely separate entities and suggests they may have all been drawing from the same deep, ancient well of knowledge. The challenge of moving these stones is immense, but the challenge of shaping them is perhaps even more perplexing. Ancient quarries reveal a mastery over materials that modern engineers would classify as extremely difficult to work. We are not just talking about limestone or sandstone, but stones like diorite and basalt, which rank between 6 and 8 on the Mohs hardness scale. For perspective, steel is around a 5.5. These are stones so hard that today we primarily use industrial diamond-tipped saws and drills to cut them. Yet, thousands of years ago, workers were not only quarrying these materials, they were shaping them into objects of stunning complexity and precision. Nowhere is this more evident than deep underground at the Serapeum of Saqqara in Egypt. Here, within a labyrinth of tunnels, rest more than 20 massive sarcophagi, each carved from a single block of granite, rose quartzite, or basalt. Each one weighs an estimated 70 to 100 tons. The outside surfaces are flawlessly smooth, with edges so sharp they seem to have been cut by a laser. But the true marvel lies inside. The interiors were hollowed out with such incredible accuracy that the surfaces are near perfect, with corners that are impeccably square and walls of a consistent thickness. How was this achieved? How do you reach inside a solid block of granite and remove the core with such control, especially with the rudimentary tools we assume were available? The accepted explanation involves a painstaking process of pounding the stone with dolerite hammers, a rock that is harder than granite. Experimental archaeologists have demonstrated that this method is technically possible. They can, over countless hours of brutal, repetitive labor, eventually pulverize the granite into a powder and remove it. But these experiments also reveal the staggering impracticality of the method for projects on the scale of the Serapeum boxes. The time and labor investment becomes almost unimaginable, raising fundamental questions about the priorities and capabilities of these ancient societies. Were they truly willing to devote decades of human effort to hollow out a single box? And if so, what drove such an immense commitment? This gap between what we believe they used and what they actually accomplished fuels the idea of lost methods. Perhaps they possessed a way to temporarily alter the stone itself. Some researchers point to the possibility of thermal shock, where a fire is built on the rock and then rapidly cooled with water, causing it to fracture in a controlled way. Others speculate about advanced abrasive slurries, using a copper saw not to cut, but to guide a mixture of water and an incredibly hard sand like crushed emery or diamond dust, effectively sanding through the solid granite over time. A more radical theory suggests the knowledge of chemical agents derived from plants that could have softened the stone's surface, making it pliable for a short period before it re-hardened. While evidence for these ideas remains elusive, the physical objects themselves stand as silent, immovable proof that our current understanding of ancient technology is incomplete. The flawless boxes in the Serapeum are not just tombs, they are direct challenges to our historical timeline, daring us to find the missing piece that explains how such impossible perfection was achieved with such apparent ease. These abandoned quarries are like time capsules frozen in the very act of creation. The most famous of these, the unfinished Obelisk in Aswan, remains a breathtaking sight, a colossal finger of granite still partly fused to the earth. Its story is told by a single, fatal crack that spiderwebs through the stone, a flaw that forced its builders to walk away from what would have been the largest obelisk ever erected. This was not a failure of will, but a triumph of quality control. It reveals that these ancient engineers possessed a rigorous standard for their work, unwilling to invest further immense effort into a piece they knew was structurally unsound. The reasons for such abandonments are a window into the pressures these societies faced. Sometimes it was a hidden geological flaw, as in Aswan. Other times, a sudden shift in political power could divert resources and labor to a new pharaoh's project, leaving a previous one to the elements. A prolonged drought or a conflict could have caused a critical shortage of food or manpower, forcing a difficult choice to halt construction. Each abandoned block tells a story not just of engineering, but of the fragile human systems that supported these grand ambitions. What can these frozen moments teach us about the knowledge that was lost? When a project is completed, we see the final, polished product. But when a project is abandoned mid-process, we see the raw methodology. We see the trenches they carved, the channels for their tools, the exact sequence of their work. It is like finding an open textbook on ancient stonecraft. Yet, these sites also pose a haunting question. If a society with such advanced knowledge could be so vulnerable to a change in leadership or a few seasons of poor harvest, how many other techniques and technologies, how many other grand projects were lost to similar upheavals? The abandoned quarries stand as stark reminders that technological progress is not a straight, inevitable line upward. It is a fragile thread, easily broken by the unpredictable tides of history, leaving behind these silent, half-born giants as monuments to what might have been. The stones were not just shaped by the landscape, they were aligned with the heavens. At sites like Stonehenge in England, the quarries themselves are oriented according to precise astronomical alignments. The massive sarsen stones were sourced from specific locations and positioned so that their arrangement marks the solstice, sunrises, and sunsets. This was far more than symbolic ritual. It was a sophisticated integration of cosmology and engineering. The act of extracting the stone may have been timed with celestial cycles, linking the very birth of the monument to the rhythm of the cosmos. Imagine the practical genius of this approach. By waiting for the summer solstice, the longest day of the year, the builders gained maximum daylight for their grueling work. The celestial calendar provided a natural, unerring schedule for organizing labor, planning the transport of stones across the rolling plains, and commemorating the start or completion of a construction phase. This was a worldview where technology and the sacred were not separate disciplines but two sides of the same coin. The precision required for these orientations is itself a marvel. To align a quarry or a monument to a specific point on the horizon where the sun only rests for a single day each year demands generations of meticulous observation. It implies the use of advanced observational tools like sighting poles or early forms of the gnomon, and a mathematical understanding of angles and geometry that we rarely attribute to so-called primitive societies. This celestial connection is a recurring thread. In ancient Egypt, the Great Pyramid is aligned to true north with an accuracy that rivals modern engineering. At the Inca site of Machu Picchu, structures are positioned to capture the sun's rays during specific equinoxes. This pattern suggests a global, or at least a widely shared, understanding that the secrets to mastering the earth were written in the stars. The very act of quarrying stone was not just a physical task, it was a cosmological event. This seamless fusion of science and spiritual practice points to a level of intellectual development that challenges our conventional timelines. It hints at a forgotten stage of human culture where the drive to build was guided by a deep, celestial wisdom, a knowledge system so complete that it orchestrated the marriage of mountain and sky. But the mastery of stone required an equal command of another element. Water, the lifeblood of civilizations, was also harnessed as a powerful tool of industry. Across ancient quarries, we find compelling evidence that water was not just for drinking or irrigation. It was an integral part of the engineering process. In the limestone quarries of Chora in Egypt, the landscape tells a story of hydrological genius. Here, massive blocks were quarried and then moved to a network of canals that connected directly to the Nile River. Instead of dragging these immense weights overland for miles, the builders may have floated them. This simple yet brilliant application of buoyancy transformed an impossible logistical task into a manageable one. The stone, once loaded onto barges, could be transported with relative ease to construction sites like Giza. This reveals a profound grasp of fluid dynamics, an understanding that the water itself could bear the burden that would crush any land-based system. This same innovative spirit appears far across the world. In Mesoamerica, evidence suggests that ancient cultures used water's unique properties in a more forceful way. By carving narrow channels into bedrock and then filling them with water, they could exploit a fundamental principle of physics. As the water freezes, it expands with tremendous force, a process that can methodically split even the hardest stone along a predetermined line. In warmer climates, they might have used wooden wedges, driving them into these cracks and then soaking them. The wood would swell, generating a steady, irresistible hydraulic pressure that pried the stone apart with surgical precision. This was not brute force, it was applied intelligence. The consistent use of these methods points to a period of intense experimentation, a golden age where natural forces were not just observed, but actively recruited into the service of human ambition. This hydrological expertise suggests a technological peak, a summit of practical knowledge where every element of the environment was understood as a potential tool. Why does this matter so deeply? Because it shows us that their innovation was not limited to one material or one technique. It was a holistic science. They possessed a unified theory of their world, seeing the connections between earth, water, and physics that allowed them to achieve the impossible. The quiet canals of Chora and the dry channels in Mesoamerican quarries are not just ancient features. They are the legacy of a forgotten engineering philosophy, one that whispers of a sophistication we are only just beginning to appreciate. The stones were not merely a resource, they were a sacred medium. Wandering through many ancient quarries, you find more than just the scars of extraction. You discover altars carved directly from the living rock, ceremonial plazas overlooking the work areas, and intricate carvings that transform an industrial site into a spiritual landscape. This was not an afterthought, it was central to the entire endeavor. At the Olmec quarries in Mexico, the act of carving a colossal head from a single basalt boulder was likely a profound ritual in itself. Each head, with its unique, powerful features, may have represented a revered leader or a divine ancestor, its creation a process that physically manifested their lineage and power into the world. The technology of moving these multi-ton monoliths from the quarry was not just a logistical challenge, it was a sacred procession, a way to transfer spiritual energy across the land. This inseparable blend of function and belief fundamentally reshapes our understanding of their motivation. Why invest generations in moving a 1,000-ton block? Perhaps because that block was not just building material, it was destined to become the eternal home of a god or the pivotal anchor for a celestial calendar. The immense effort becomes comprehensible when we see it as an expression of faith, a communal act of devotion that unified the entire society. This points toward a holistic world, entirely different from our own modern separation of science and spirit. For these ancient cultures, innovation in stonework was a spiritual discipline. The precision of their cuts, the mastery of physics, the understanding of geology, all of these were pathways to engaging with the divine order of the universe. The quarry was their temple, and their tools were extensions of their belief. This symbolic dimension does not diminish their technological achievements, it elevates them. It suggests that our drive to build and create may have its deepest roots not in pure utility, but in a fundamental human need to connect with something greater than ourselves, to leave a mark not just on the land but on the cosmos itself. Behind every colossal stone block stood a society organized on an equally massive scale. The quarries themselves were complex engines of human endeavor, demanding far more than just strong arms and simple tools. They required the seamless coordination of specialized labor, a steady flow of supplies, and a sophisticated administrative system to manage it all. The ruins of the Roman quarries at Carrara, Italy, offer a clear glimpse into this ancient industrial machine. Here, inscriptions carved into the stone speak of a detailed hierarchy, from the skilled artisans who cut the marble to the overseers who directed the work and the clerks who tracked every block extracted and shipped. This was not a chaotic mob of laborers, it was a structured, professional workforce dedicated to a single, monumental task. Such an operation could not function without advanced planning and meticulous record-keeping. Someone had to calculate the food and water needed for thousands of workers, organize the transport of tools and materials, and schedule the shipment of finished blocks to construction sites across the empire. This level of logistical control points to a societal maturity that we rarely associate with the ancient world. It reveals a culture with a powerful central authority, a functioning bureaucracy, and a deep understanding of project management. This challenges the very idea of a primitive society. How could a culture we consider technologically basic simultaneously possess the administrative genius to run what were essentially the first multinational corporations? The existence of these organized systems suggests that the missing stage of technology might not be limited to physical tools alone. Perhaps the true lost innovation was a suite of sophisticated administrative techniques, a science of organization that enabled the planning and execution of projects that still baffle us today. The stones are not just evidence of engineering prowess, they are the physical results of a forgotten social technology, a blueprint for human cooperation on a grand scale that allowed our ancestors to achieve the impossible. The most enduring image of pyramid construction is a vast ramp of earth and rubble, a colossal slope built to drag stones upward. Yet, the physics of this idea begins to strain under the weight of the final stones. To place the capstone of the Great Pyramid, a granite block weighing dozens of tons, a ramp would have needed to rise at a shallow angle for nearly a mile in length. The volume of material required to build such a structure would have rivaled the pyramid itself, creating a logistical nightmare that seems at odds with the project's elegant precision. Where is the evidence for the removal of this mountain of ramp material? The site itself is silent. This absence forces a difficult question. Could simple ramps, levers, and ropes really account for the placement of millions of blocks with such flawless accuracy? The sheer efficiency of the work hints at something more sophisticated, a mechanical advantage we have not yet fully grasped. Some researchers propose the use of internal spiral ramps, a theory that solves the external debris problem but introduces complex challenges of its own, particularly in maneuvering the largest cornerstone blocks around tight corners. Other ideas venture into more speculative territory. Could they have used a system of water-filled counterweights where the buoyant force of water in sealed shafts was harnessed to lift immense loads? Or perhaps they employed a form of crane technology, using wooden frameworks and ropes to walk the stones upward in a series of controlled, incremental steps. The most intriguing, though least evidenced, theory involves the concept of acoustic levitation, where specific sound frequencies might have been used to reduce the effective weight of the stone, making it easier to move. While evidence for such advanced methods is sparse, the architectural achievement itself stands as a powerful argument for their possibility. The placement of the granite beams in the King's Chamber, high within the Great Pyramid, is a case study in this precision. These stones, weighing up to 70 tons each, were not just dragged into place, they were lifted, turned, and set with an accuracy of a fraction of an inch. This was not a feat of brute force, but of controlled, repeatable mechanical process. It points toward a period of intense innovation, a golden age of practical physics where inventors and engineers discovered principles of leverage and balance that were later lost to time. The silence of the archaeological record regarding these tools is deafening. It suggests that the true machinery of the ancients may not have been built of stone and metal, but of knowledge, a system of applied science so effective that it left behind only its magnificent, gravity-defying results for us to ponder. These seamless stone walls stand as the ultimate expression of this lost engineering. High in the Andes at Sacsayhuamán, a fortress built from colossal limestone blocks, you can run your hand over a join where two giant stones meet. The fit is so impossibly tight that not even the thinnest blade of a razor can find its way between them. This is ashlar masonry, a construction method that uses no mortar, no cement, no glue of any kind. The entire immense structure relies solely on the perfect, interlocking geometry of the stones themselves. How could such precision be achieved on blocks weighing hundreds of tons with only the simple tools we acknowledge? The surfaces are not just flat, they are often subtly convex or intricately keyed, creating a three-dimensional puzzle that locks together under its own weight. This was not just about aesthetics, it was a brilliant and deliberate engineering solution. The entire wall becomes a single, flexible entity. When an earthquake strikes, instead of cracking and crumbling like a rigid, mortared wall would, these interlocking stones shift and sway as one, then settle back into their original, perfect alignment once the shaking stops. This reveals an understanding of seismic activity and structural dynamics that feels incredibly advanced. To accomplish this, the builders must have employed a system of measurement and replication that borders on the industrial. They likely used standardized templates, perhaps made of wood or stone, that acted as physical guides. A master template would be placed on a finished block, and the next stone would be painstakingly shaped to match its unique, irregular contours. This process implies a production line mentality where every block, regardless of its size, was crafted to fit one specific spot in the grand design. The knowledge required goes far beyond simple stone cutting. It speaks of a deep familiarity with geometry, of an ability to visualize complex, negative spaces in 3 dimensions. This level of technical sophistication, appearing in cultures separated by vast oceans, is what fuels the idea of a shared, ancestral knowledge. Was this technique developed independently through millennia of trial and error, or does the flawless precision we see at Sacsayhuamán and in Inca sites across Peru point to a much older, refined system of construction that was inherited from a forgotten precursor culture, a civilization that had already mastered the silent language of stone? The challenge of quarrying only deepened when the stone itself was not uniform. Imagine the immense difficulty of cutting a block of limestone, a relatively soft stone, only to strike a hidden nodule of flint, a material far harder than steel. This was the daily reality for ancient miners at sites like Grimes Graves in England. Here, the landscape is pockmarked with hundreds of shafts sunk deep into the earth, not for precious metals, but for the high-quality flint hidden within the chalk. The miners did not simply hack away at the earth. They used the shoulder blades of oxen as shovels and crafted picks from the strong, branched antlers of red deer. With these seemingly primitive tools, they followed the narrow, twisting seams of premium flint with the precision of a surgeon, carefully avoiding the brittle or flawed stone. This was not a crude operation. It was a masterful application of geological intelligence. They understood how the flint layers fractured, how to apply pressure at just the right point to prise out a perfect core, and how to navigate a material landscape of wildly varying hardness. This empirical knowledge of fracture mechanics is a sophisticated science, one we assume is modern. How did they acquire such a nuanced understanding of their materials without formal training? Their success suggests generations of accumulated, hands-on experience, a living library of stone lore passed from one worker to the next. This ability to work with heterogeneous materials points to a broader, more adaptable technological toolkit than we often credit. Perhaps the lost methods we seek were not a single magical technique, but a vast repertoire of solutions for every conceivable stoneworking problem. They knew when to use force, when to use patience, and when to use the natural weaknesses in the stone to their absolute advantage. The silent, dark shafts of Grimes' graves are a testament to this flexible, brilliant ingenuity, proving that their mastery was not just over one type of stone, but over the very character of the earth itself. The very stone itself holds the final, unerasable clues. On the surfaces of granite blocks at Giza and on the andesite monoliths of Peru, if you look closely, you can see the faint, ghostly marks left behind by the tools that shaped them. These are not the rough, chipped scars you would expect from pounding with stone hammers. Instead, they are often long, continuous grooves, sometimes with a fine, almost polished striation running along their length. The physics of this is undeniable. To cut a clean, straight groove into granite, a material harder than steel, the cutting tool must be even harder. The soft copper chisels and bronze saws we find in museum cases simply could not have made these marks. They would have blunted into useless nubs before making even a shallow scratch. This forces a startling conclusion. The ancient craftsmen must have been using something else, something far more advanced. Experimental archaeologists have tried for decades to replicate these precise cuts using only the tools we officially attribute to these cultures. They use copper saws with sand and water as an abrasive, a method that does work but slowly, and it leaves a very different kind of mark, a wide, frosted channel, not a narrow, defined groove. The results never quite match the ancient originals. There is a persistent gap between what our experiments can achieve and what the stones themselves prove was done. This discrepancy points toward a missing chapter in material science. Perhaps they had developed a way to case-harden their copper tools, creating a thin, diamond-hard edge through a specialized tempering process we have not yet rediscovered. Or maybe they were using alloys we do not commonly associate with their era, like a form of hardened bronze with rare mineral additives that gave it extraordinary durability. The most compelling evidence comes from the cut marks that show a level of micro-precision. Some grooves in granite are so consistent in their depth and width that they suggest the use of a powered, rotating tool, or at the very least, a saw blade that was incredibly rigid and resistant to wear. This has led some researchers to propose the use of abrasive slurries infused with crushed diamond dust or corundum, the mineral that forms rubies and sapphires. A copper blade, in this scenario, would act merely as a delivery vehicle, pressing the incredibly hard abrasive particles against the stone, effectively sanding through it with phenomenal efficiency. This would explain the fine, parallel striations and the polished appearance of some cuts. Yet, if this was their method, where is the archaeological evidence for the mass mining and processing of these super-hard abrasives? The absence is as telling as the marks themselves. It suggests an industry, a supply chain, and a technical knowledge that has vanished almost without a trace. The stones silently testify to a technology that was not just different, but in some ways superior to what we believed possible. They challenge us to accept that the true tools of the pyramid builders may not be sitting in a display case, but are recorded only in the unyielding granite, waiting for us to finally understand their message. The silent testimony of the stones extends from the quarries to the open sea. Many of the most iconic ancient monuments required a final, daring journey across water. The colossal moai of Easter Island were carved from volcanic rock inland, yet their final resting places are coastal platforms, often miles from the quarry. This meant maneuvering the multi-ton statues across the island, and for some, a precarious voyage on wooden rafts to offshore islets. Similarly, the smaller bluestones of Stonehenge in England were sourced from the Preseli Hills in Wales, a journey of over 150 miles that almost certainly involved crossing the unpredictable waters of the Bristol Channel. The challenge here is not just about building a boat that floats. It is about building a vessel with the stability and capacity to carry an unbalanced, incredibly dense load through waves and currents without capsizing. Imagine the process of loading an 80-ton stone statue onto a raft made of logs. The slightest miscalculation in balance would send the entire operation to the bottom of the sea. This required a profound, almost intuitive understanding of naval architecture. Researchers propose the use of large, buoyant reed boats, like those depicted in ancient Egyptian art, or sophisticated wooden vessels built from massive timbers. These were not simple, hollowed-out logs. They would have needed a carefully engineered hull design to distribute the immense weight evenly, preventing the craft from buckling or becoming unstable in open water. This maritime capability points to a missing chapter in our history of technology. It suggests that ancient peoples possessed a masterful grasp of hydrodynamics and weight distribution, principles we formally codified only centuries later. They were not just stoneworkers, they were naval engineers who understood how to make water itself their ally, using its buoyant force to solve a problem that would be overwhelming on land. The successful transport of these megaliths over water stands as one of the most compelling and overlooked arguments for a lost stage of human ingenuity. The very environment that provided the stone also dictated the rules of its extraction. Ancient quarries were not placed for convenience, they were forced engagements with the planet's most demanding landscapes. In the searing heat of the Egyptian desert, where water was as precious as gold, workers developed ingenious methods that turned their surroundings into tools. They likely used the desert's own abundant sand, mixed with water as a polishing agent, dragging a heavy stone block back and forth over a wet, sandy surface would have efficiently smoothed its face, a brilliant adaptation that used minimal resources for maximum effect. This was a technology born of necessity, a direct response to the unyielding sun and the scarcity of everything but rock and sand. Now shift that scene entirely. Imagine a quarry in the dense, humid jungles of Mesoamerica or Southeast Asia. Here, the constant threat was not dryness, but water itself. Torrential rains could turn a worksite into a muddy death trap, where colossal stones risked slipping uncontrollably, or where the very walls of the quarry could be undermined by erosion. The technologies developed here had to solve entirely different problems. Workers might have engineered complex drainage systems to channel water away from the workface, or they may have used the jungle's own resources, creating vast networks of vines and wooden rails to provide secure footing and controlled movement for the stones. This pragmatic innovation, tailored to the specific whispers and shouts of the local climate, reveals a deep, intimate dialogue between the builders and their world. They were not conquering nature, they were learning its language and collaborating with its forces. This environmental specialization is a crucial piece of the puzzle. A technique perfected in the dry desert for moving stones on slick, wet clay would have been useless there, and vice versa. This means that the technological peaks of the ancient world were not a single, monolithic achievement. They were a diverse constellation of brilliant, localized solutions. The knowledge of how to work stone in the rainforest was a unique branch of engineering, as advanced in its own context as the desert methods were in theirs. When a society that mastered quarrying in a specific environment declined or was displaced, that particular branch of technology could snap off, its secrets fading away with the people who held them. The stones left behind in these challenging locations are more than monuments. They are the legacy of 1,000 different conversations with the earth, each one a testament to a forgotten technological peak that we are only just beginning to appreciate. Beyond the sheer scale of construction lay a world of miniature perfection. The ancient mastery of stone extended from 100-ton blocks to fragments of breathtaking beauty, quarried for the delicate art of inlay. In the royal workshops of ancient Egypt, artisans crafted pectorals and funeral masks adorned with lapis lazuli, a deep blue stone flecked with gold that was more precious than any metal. This material did not come from the local deserts. It was sourced from a single, remote source, the Sacsayhuamán mines in the mountains of what is now Afghanistan. The journey of this stone was an epic in itself, traveling thousands of miles across deserts and seas through a vast, interconnected trade network. This was not a simple exchange of goods, it was a testament to a globalized demand for aesthetic excellence. To transform a rough chunk of lapis into a perfectly shaped inlay for the eye of a Tutankhamun funerary mask required tools of astonishing precision. The stone had to be cut into thin slices, then shaped into tiny, intricate forms using fine saws and drills that could operate on a scale of millimeters. How did they achieve such control? The survival of these artifacts, with their crisp edges and flawless surfaces, points to the use of advanced abrasive pastes. Craftsmen likely used copper or bronze blades, not to cut directly, but to guide a slurry of water and an incredibly fine powder, perhaps made from crushed emery or quartz sand. This would have acted like a liquid sandpaper, allowing them to saw and carve with a delicacy that rivals modern jewelers. This technological refinement was not unique to Egypt. Far across the world, in the heart of Mesoamerica, the Olmecs and Maya pursued a similar obsession with jade. This stone is even tougher than steel, yet they carved it into elaborate celts, masks, and beads with a level of detail that is simply baffling. They used tubular drills made from hollow reeds or bone, rotating them with a bow while feeding a slurry of hard abrasive into the cut. This method allowed them to drill clean, precise holes and create complex hollow forms, a process that would have required immense patience and a steady, skilled hand. The existence of such delicate workforces a profound realization. The drive for beauty was a powerful engine for technological innovation. The same culture that could move a mountain of stone to build a pyramid also developed the micro-tools to set a sliver of turquoise into a golden scarab. This dual focus on brute strength and delicate finesse suggests a society operating at a high level of technological integration. The quarries for these decorative stones were not just holes in the ground. They were the starting point for a chain of artistry that linked the miner in a distant mountain to the royal artisan in a sun-baked workshop. This cultural valuation of aesthetics, this willingness to pour immense resources into the pursuit of beauty, may have been the very soil in which a wider technological flowering took root. When a society prizes such intricate skill, it fosters specialization, experimentation, and the development of tools that push the very boundaries of what is possible. The silent, gleaming beauty of a lapis lazuli inlay is more than just decoration. It is a tiny, perfect window into a lost world of innovation, where the quest for magnificence in the small may have been the key to achieving the impossible in the grand. This drive for efficiency transformed quarries into the first assembly lines. Deep within the quarries that supplied the Roman Empire, we find evidence not of unique artistry, but of systematized repetition. The blocks extracted for projects like the Colosseum or the vast network of aqueducts were not one-of-a-kind masterpieces. They were standardized units, cut to consistent sizes and shapes with a remarkable degree of uniformity. This was not about celebrating the individual craftsman. It was about achieving a new kind of speed and scale in construction. A worker did not need to be a master stonemason to place a block. He simply needed to follow a pattern, knowing that every piece would fit because it was made to the same exact template as the one before it. This shift hints at the use of physical guides, early jigs or molds that held a stone in place while it was cut or shaped, ensuring every block that came out was a perfect copy of the last. This standardization is the bedrock of mass production, a concept we tightly associate with the factories of the 19th century, yet here it is fully formed in the ancient world. It points to a proto-industrial mindset, a conscious move away from custom craft and toward a system of interchangeable parts. This approach dramatically lowered the skill threshold required for each individual laborer. A single master could set the template, and teams of workers could then replicate that design endlessly, turning the chaotic process of stone cutting into a predictable, streamlined operation. The implications are profound. This was not just a clever way to build faster, it was a different way of organizing human effort and technological knowledge. It suggests that the ancient world was flirting with an industrial revolution of its own, one based on stone and muscle rather than steam and steel. Why did this system not continue to evolve and transform the world? Was it lost in the political and social upheavals that dissolved the Roman Empire, its techniques scattered and forgotten? Or was it a technological path that simply reached its natural limit without the discovery of new power sources? The standardized blocks left behind in these quarries are silent witnesses to a road not taken, a forgotten prototype for a world that could have been. The quarry floor holds another secret, one written in soot and steam. Evidence is mounting that ancient workers did not just fight the stone with blunt force, they conversed with it using fire and water. From the granite quarries of India to the ancient mines of Scotland, researchers have identified surfaces scarred by intense, localized heat. The method was as brilliant as it was simple. Workers would build a controlled fire directly against the rock face, heating the stone for hours. Then, just as the rock reached its peak temperature, they would douse it with cold water. This sudden, violent change creates what is known as thermal shock. The outer layer of the stone contracts rapidly while the inner core remains expanded, generating immense internal stress that fractures the material along a clean, predictable line. This was not a haphazard process. It required a deep, intuitive understanding of the stone's specific properties. Different types of rock have different thermal tolerances. Granite, for instance, reacts differently than limestone. The timing had to be perfect. Apply the water too soon, and the fracture would be shallow. Wait too long, and the stone could develop a web of unwanted cracks, ruining the entire block. This technique transformed an impossible task into a manageable one. Splitting a 50-ton block from the living bedrock with only stone hammers would be a monumental, perhaps insurmountable, challenge. But with thermal shock, the rock would practically split itself, requiring only minimal prying with wooden wedges to finish the separation. This represents a fundamental leap in thinking. It shows these workers were not just laborers, they were practical physicists and chemists, manipulating the fundamental properties of matter to achieve their goals. The widespread use of this method suggests it was part of a broader, sophisticated pyrotechnical knowledge. The same culture that mastered fire setting in quarries likely also possessed advanced skills in smelting metals, creating glazes for pottery, and perhaps even in early forms of glassmaking. This points to a technological ecosystem where innovation in one field, like metallurgy, directly fueled advances in another, like megalithic construction. The quiet, blackened surfaces of these quarries are not just evidence of fire, they are the remnants of a controlled, chemical conversation with the earth, a dialogue we are only now learning to hear. The stone itself could sing. Deep beneath the island of Malta, the hypogeum of Hal-Saflieni descends into a labyrinth of chambers carved from Globigerina limestone. In one particular room, known as the Oracle Chamber, a low voice spoken against the wall resonates through the entire space, the sound amplifying and transforming into an echo that seems to come from everywhere at once. This was no accident of geology. The builders of this underground complex specifically quarried and used stones from strata known to possess these unique resonant properties. They were not just architects of space, they were engineers of sound, selecting their materials with an ear for vibration as much as an eye for form. This acoustic intention reveals a layer of technological purpose we are only beginning to appreciate. How did they identify these special stones while still in the quarry? The method was likely deceptively simple. A quarry master would walk along the exposed rock face, tapping different sections with a hammerstone and listening intently to the tone that reverberated back. A dull thud would indicate a dense, flawed block unsuitable for their purpose, but a clear, bell-like ring would signal a stone with a homogeneous crystalline structure, one capable of carrying sound waves with perfect clarity. This act of listening was a sophisticated form of material science, a practical test that required a trained ear and a deep, empirical understanding of how sound travels through different mediums. This focus on non-visual properties points toward a holistic worldview, a technology that engaged all the senses. Construction was not merely a visual or structural endeavor, it was an auditory one. In a ceremonial space, the ability to make a spoken word or a chanted prayer resonate through a chamber would have profoundly deepened the spiritual experience, creating a sense of awe and connection that static architecture alone could not achieve. Some researchers suggest that certain resonant frequencies could even induce specific states of awareness, making the architecture an active participant in ritual practices. This ancient acoustic engineering challenges our modern, often silent, interpretation of these sites. We see the stones, but we do not hear their original purpose. The silent, perfectly fitted blocks of other ancient sites may also hold this hidden sonic dimension, a lost frequency waiting to be rediscovered. The quest for the perfect tone in a Maltese quarry whispers of a forgotten technological principle, one where the true masterpiece was not just in the shape of the stone, but in the sound it was chosen to carry. Even the most perfectly planned projects demanded on-site adjustments. Across the ancient world, the evidence of repair and modification reveals a technology that was dynamic, not static. At the great citadel of Mycenae in Greece, for example, some of the massive limestone blocks in the famous Lion Gate show clear signs of being reworked after they were set in place. A stone might have developed a hidden crack under the strain of its own weight, or perhaps the initial fit was not quite perfect. Instead of dismantling the entire wall, the masons returned with their tools to reshape the stone in situ, carving new angles or shaving down a protruding edge to ensure a seamless, stable fit. This was problem-solving on a monumental scale, a testament to a living, breathing tradition of stoneworking where knowledge was not a rigid set of rules, but a flexible craft continuously refined by real-world challenges. This ability to modify multi-ton stones already locked into a structure implies a toolkit and a skill set of remarkable versatility. They needed tools that could cut and polish in tight spaces, and the confidence to know they could correct a flaw without starting over. It speaks of a deep, accumulated wisdom, a long lineage of masters and apprentices passing down solutions for every conceivable problem. What does this flexibility tell us about the loss of such knowledge? When a society experiences a profound social collapse, a war, or a prolonged famine, it is not just the grand monuments that fade. The first things to vanish are the subtle, practical arts, the nuanced tricks of the trade that are never written down but live in the hands of the craftsmen. The knowledge of how to stabilize a shifting foundation block or how to resurface a damaged obelisk would have been among the most fragile and specialized of all. This evidence of ancient repair is a powerful reminder that their technology was a living system, one that could adapt and evolve. Its disappearance suggests not a single catastrophic loss, but a slow fading, a quiet unraveling of 1,000 intricate skills that together formed the fabric of a forgotten age of engineering genius. Centuries later, the great cathedral builders of medieval Europe would rediscover some of these ancient secrets. The stonecutters' guilds, protectors of closely held techniques passed from master to apprentice, employed methods that echo those of their distant predecessors. They too used wooden wedges and water to split stone from the quarry face, and they understood the importance of reading the bedrock's natural grain. This faint but clear thread of continuity suggests that a core body of practical knowledge somehow survived the collapse of empires, preserved in workshops and oral traditions across generations. Yet something fundamental was different. While the cathedrals are breathtaking achievements of faith and engineering, their stonework rarely matches the impossible precision of a site like Sacsayhuamán or the Serapeum. The joints between blocks, though skilled, are filled with mortar. The surfaces, though beautifully carved, do not possess that machined flatness found on much older granite boxes. The scale of individual stones, while impressive, does not approach the 1,000-ton giants of Baalbek. This points not to a lack of skill or dedication, but to a tangible degradation of technological capability over time. The medieval masons were brilliant inheritors, working with a diluted version of a much older, more refined science. What specific abilities faded away? The evidence points to a lost mastery over the hardest stones. The intricate working of granite, basalt, and quartzite, so common in the ancient world, becomes remarkably rare. Later cultures often reverted to using softer, more workable materials like sandstone and limestone. The secret to creating those seamless, mortar-less joints, the kind that lock together and withstand earthquakes, seems to have vanished entirely. This was not just a loss of technique, but likely a loss of the tools themselves. Perhaps the guilds no longer possessed the formulas for advanced metal alloys or the recipes for super-hard abrasive slurries that could slice through diorite. The historical trajectory is difficult to ignore. It suggests that human technological progress is not a simple, upward-sloping line. There can be peaks and valleys, and sometimes a peak is so high that its summit is later mistaken for a work of the gods. The quiet, persistent gap between what the ancients achieved in their quarries and what even the most advanced later societies could replicate stands as one of the most compelling arguments for a missing chapter, a golden age of practical innovation whose most advanced tools and methods were ultimately lost to the ages, leaving only their stone fingerprints behind. The stones themselves became instruments of celestial observation. Far from simple markers, quarried blocks were positioned with such exacting precision that they transformed entire landscapes into vast astronomical clocks. At Nabta Playa in the Egyptian desert, a complex arrangement of shaped stones sits under the immense Saharan sky. These were not randomly placed, specific stones, carefully selected for their durability and then shaped in the quarry, align with the rising sun of the summer solstice and the positions of key stars. This was a functioning calendar carved from the earth, predicting the coming of seasonal rains crucial for survival in a challenging environment. The process demanded more than just stone masonry. It required a deep, generational understanding of the sky's movements, a knowledge so precise it could be encoded into the very placement of multi-ton rocks. The quarry workers were not just extractors, they were partners in a scientific endeavor, choosing stones that would not weather or shift over centuries, ensuring the alignments remained true for generations to come. This fusion of quarrying and astronomy is echoed on the Mediterranean island of Malta. Within the Najdra temple complex, limestone slabs quarried from local sites frame the equinox sunrise with breathtaking accuracy. On those specific mornings, the first rays of the sun slice through the main doorway, illuminating a central stone slab in a dramatic display of light and shadow. To achieve this, the builders needed an advanced grasp of geometry. They had to calculate angles, understand solar trajectories, and then translate those abstract calculations into the physical cutting and positioning of enormous stones. The quarrying process itself was tailored to this higher purpose. Stones were likely selected for specific visual properties, perhaps a particular grain or color that would interact with sunlight in a desired way. This represents a technology that seamlessly blended heavy construction with delicate scientific instrumentation. It suggests the existence of a lost tradition where the architect, the astronomer, and the quarry master were one and the same. What kind of society could so perfectly unite the practical and the theoretical? This points toward a culture where empirical observation was the driving force behind technological innovation, a civilization that looked to the stars not just for myth, but for measurable, actionable data, and then built its world in perfect alignment with that cosmic clock. The chisel and hammer were not the only tools that shaped these stone giants. They were powered by the heartbeat of an entire community. Across the ancient world, the back-breaking labor of quarrying was often transformed into a social and even a celebratory event. In ancient Mesopotamia, intricate cylinder seals depict not scenes of grim toil, but of vibrant processions. We see lines of people working in unison to haul massive stones, their efforts framed within what appears to be a festival atmosphere. This was more than just a clever way to get work done. It was a societal technology. By embedding the hard work within a ritual or a communal celebration, leaders could mobilize a vast labor force that would otherwise be impossible to assemble and sustain. These gatherings became living libraries of technique. A young worker pulling on a rope alongside a seasoned master would learn the precise rhythm needed to move a colossal block without fracturing it. He would hear the chants used to coordinate a lift and observe the subtle ways to position a lever for maximum effect. This was how complex knowledge was transferred across generations, not through written manuals, but through shared experience and oral tradition. The organization required for these events was a marvel in itself, coordinating the food, shelter, and safety for thousands of people, all while directing a precise engineering operation, points to a sophisticated administrative system. This social machinery, the ability to inspire, organize, and unite a population toward a single, monumental goal, may have been the most advanced technology they possessed. While their physical tools have largely vanished, the legacy of this communal spirit is etched into the very scale of their achievements, reminding us that the greatest monuments were built not just with stone, but with a shared sense of purpose that moved mountains. The stone itself became a language. Beyond structural integrity, ancient builders selected specific stones for their color and texture, embedding layers of symbolic meaning directly into their architecture. In the sun-baked deserts of Egypt, the choice of red granite for royal sarcophagi and temple elements was no accident. This fiery, crystalline stone was intrinsically linked to the sun god Ra, its deep crimson hue seen as a physical manifestation of his life-giving and fearsome power. To place a pharaoh's remains within a coffin of red granite was to encase them in the very substance of the divine, ensuring a symbolic rebirth with the rising sun each day. This was not a superficial decoration, it was a theological statement carved from the earth. The quest for such specific materials transformed the quarry from a simple workshop into a landscape of profound spiritual significance. Quarry masters needed a geologist's eye capable of reading subtle shifts in the bedrock to locate these rare, visually distinct layers. They were not just cutting rock, they were harvesting meaning. This aesthetic imperative drove technological innovation in surprising ways. The ability to cleanly extract large, flawless slabs of a specific colored granite without fracturing it required a level of precision that simple block quarrying might not demand. The techniques for polishing these stones to a high, reflective sheen, making the color gleam under the sun, became a guarded art. This symbolic drive created a feedback loop, where the cultural desire for a certain material pushed the boundaries of extraction and finishing technology, ensuring those advanced methods were preserved and passed down through generations. The emphasis on material qualities reveals a cultural framework where the highest purpose of technology was to manifest ideological concepts in tangible, enduring form. A black basalt threshold in a Mesopotamian temple might have been chosen for its association with the underworld, while a pure white limestone facing for a pyramid complex spoke of celestial purity and light. This nuanced, holistic approach to materials, where every stone was selected for both its physical and its metaphysical properties, may be a defining characteristic of that missing technological stage. It suggests a world where engineering and esoteric knowledge were not separate disciplines, but intertwined strands of a single, sophisticated understanding, a forgotten science where the very soul of a culture was quarried from the mountainside. The silent pathways between quarry and monument tell their own story of precision. Moving a 1,000-ton block is one thing, but knowing exactly where to place it, often miles away and on uneven ground, required a different kind of genius altogether. The evidence points to a lost science of ancient surveying and mapping, a discipline of measurement that guided these colossal projects with unerring accuracy. At the Roman quarries of Mons Claudianus in Egypt, the desert floor is a scattered archive of this planning. Inscriptions carved into the rock detail the dimensions of specific blocks, their intended destinations, and even the names of the work crews assigned to them. Small artifacts found nearby, fragments of tools and personal items, hint at the presence of administrators who oversaw this immense logistical operation. This was not a haphazard effort. It was a meticulously mapped campaign of extraction, a clear indication that the builders worked from detailed plans. They would have needed to measure vast distances across broken terrain, calculate the gentle slopes necessary for moving massive weights, and ensure that the final construction site was perfectly level and oriented. How did they achieve such cartographic precision without modern instruments? they almost certainly used tools like the groma, a simple but brilliant device for sighting right angles over long distances. Or they may have employed water levels, using the immutable property of water to find a true horizontal plane, even across a chaotic landscape. This mathematical technology was the invisible framework upon which the physical stones were hung. The loss of this precise cartographic knowledge is a quiet catastrophe in the story of human innovation. Later societies, even the great cathedral builders, often struggled with the sheer scale and alignment of ancient projects. They could build beautifully, but they seemed to have lost the master blueprint, the systematic approach to orchestrating a continent-spanning construction project. The grandest monuments of antiquity were not just triumphs of muscle, they were victories of measurement, testaments to a time when humanity had already learned to draw the world to scale, and then build it exactly as they had planned. The mastery of stone extended far beyond temples and tombs, reaching into the very arteries of ancient cities. Many of the most precisely cut stones ever quarried were destined not for grand monuments, but for the life-giving networks of water management. Aqueducts, cisterns, and public fountains all demanded a specific kind of stonework, one that could withstand constant pressure and prevent precious water from seeping back into the earth. The Roman aqueducts stand as the ultimate expression of this hydraulic engineering. Their channels, built from quarried stone and waterproof cement, snake across valleys and through mountains, maintaining a gentle, precise gradient for dozens of miles. Each stone in that conduit was not merely a block, it was a component in a massive, flowing machine. The joints between these stones had to be perfectly fitted and sealed, a task requiring a level of precision that prevented leaks and resisted the relentless force of moving water over centuries. This was an applied science of fluid dynamics, carved directly into granite and limestone. The quarry workers and masons understood that the shape and finish of the stone directly influenced the flow. A rough, irregular surface would create turbulence and friction, slowing the water and encouraging mineral deposits that would eventually clog the channel. Therefore, the stones for these water systems were often dressed to a smooth, almost polished finish on their interior faces, a detail that reveals a profound, practical understanding of how water interacts with solid surfaces. This specialization points to a technological peak that was intensely pragmatic. It was an engineering tradition tailored to the needs of growing urban populations and expanding agriculture, a clear sign of a society solving complex problems of infrastructure and public health. The existence of such refined hydraulic stonework across different cultures, from the subterranean aqueducts of Persia to the intricate fountains of Petra, suggests this was not an isolated Roman genius, but perhaps a widely shared fragment of a much older, lost tradition of civil engineering. The quiet, enduring flow of water through these ancient stone channels is a testament to a forgotten age where technology served not just the gods, but the daily lives of every citizen. The quarries themselves were the first classrooms. Scattered across these ancient stone workshops, the evidence of learning is literally carved into the walls. Alongside the masterful, clean cuts of an experienced hand, you find rougher, more hesitant marks, a groove that wavers off its intended line, a corner that is not quite square, a block with a fractured edge from a misapplied hammer blow. These are not errors, but the fossilized lessons of a structured apprenticeship. A master craftsman would guide a novice, demonstrating the precise angle to hold a tool or the exact rhythm needed to split a stone along its natural grain. This direct, hands-on transfer of skill was the lifeblood of their technological tradition. It ensured that the nuanced art of quarrying, the intimate knowledge of stone, was not lost with a single generation, but was woven into the fabric of the culture itself. This system of knowledge was both its greatest strength and its most profound vulnerability. The continuity of these techniques relied entirely on the unbroken chain of teachers and students. When that chain was shattered by a sudden invasion, a devastating outbreak of illness, or a forced migration, the consequences were catastrophic. The complex methods perfected over centuries could vanish in a single lifetime. The deep understanding of how to identify the perfect stone, how to apply thermal shock with precision, or how to maneuver a 70-ton block using counterweights, these were not written in books. They lived in the hands and minds of the artisans. Once the training was interrupted, that living library was lost forever. This explains the puzzling technological regression we see in the archaeological record. Later societies, even with the same materials and the same ambition, often could not replicate the flawless precision of their predecessors. They were attempting to rebuild the engine without the blueprints, possessing the parts but not the knowledge of how they fit together. The disappearance of advanced quarrying methods becomes a story not of forgotten tools, but of broken connections. It reveals that the true foundation of ancient innovation was not just brilliant engineering, but the resilient social structures that nurtured it, the quiet, patient passing of wisdom from one set of hands to the next, a fragile thread that, once cut, left the stones silent for 1,000 years. The same stone that built temples was also shaped for war. Across the ancient world, the drive for security forged a brutal, brilliant school of engineering, one that transformed quarries into factories of defense. Consider the Cyclopean walls of Mycenae in Greece, built from limestone blocks so immense that later generations believed only mythical giants could have lifted them. These were not merely stacked stones, they were a calculated response to the threat of siege engines and battering rams. Each colossal block was quarried and shaped with a specific defensive purpose. The builders intentionally selected irregular, polygonal shapes, jigsaw puzzling them together into a wall with no straight, continuous lines. Why this deliberate complexity? Because a curved, interlocking joint dissipates the energy of an impact far more effectively than a straight, vertical seam. A blow from a ram would be absorbed and redirected across the entire face of the wall, rather than concentrating its force on a single, vulnerable point. This was applied physics on a monumental scale, a masterclass in structural mechanics born from necessity. This defensive imperative pushed quarrying technology to its absolute limits. It was no longer enough to extract a large block. Now it had to be a specific, often irregular shape, with multiple angled faces that would lock perfectly with its uniquely shaped neighbors. The precision required was staggering. A miscalculation of a single angle could compromise the integrity of an entire section of fortification. This pressure to build stronger, faster, and smarter likely accelerated innovations in quarrying. The knowledge of how to split stone along complex, non-linear planes and how to dress its surface to a perfect, load-bearing fit would have become a state secret, a technology guarded as fiercely as the walls themselves. But this creates a profound historical paradox. The very conflicts that spurred this technological peak also contained the seeds of its loss. When a society like the Mycenaean civilization faced a period of decline, perhaps through internal conflict or external invasion, the specialized guilds of defensive stonemasons would have been among the first casualties. The intricate knowledge of how to shape a bastion to withstand a multi-year siege is not a skill that can be easily preserved in times of peace or social collapse. The technology of defense, so brilliantly honed in the quarry, faded away when the immediate, existential threats that demanded it finally receded into the quiet of history. The rhythm of the ancient world was not a frantic, constant beat, but a measured pulse aligned with the seasons, Deep within the quarries, we find evidence of this deliberate tempo etched into the very stone. In the limestone beds of Egypt and the high-altitude quarries of the Andes, the work was not continuous year-round. Instead, it peaked during the dry months or the cooler periods, when the climate was most favorable for the grueling labor and, more importantly, for transporting the fruits of that labor. Imagine the onset of the dry season. The intense summer heat that would have made heavy work dangerous recedes, and the hardened ground becomes a stable highway for moving colossal weights. The rivers, fed by seasonal rains, are at their highest, ready to bear the immense burden of stone on barges. This was not a simple reaction to the weather, it was a sophisticated, premeditated strategy. It reveals a culture that planned its industrial output not in days or weeks, but in seasons and years. This cyclical approach required a deep understanding of the local environment and an incredible capacity for foresight. They had to quarry and prepare enough stone during the working season to supply construction projects for the entire year. This implies the existence of organized storage yards, protected areas where finished blocks waited patiently for their journey, a testament to a managed, sustainable use of resources that thought in generational terms. This synchronization with nature extended far beyond the quarry phase. The entire operation was woven into the fabric of agricultural life. The same society that needed thousands of workers to move stone also needed those same hands to plant and harvest crops. The quarrying season naturally fell during the agricultural off-season, when the labor force was available. This was a brilliant societal adaptation, a way to mobilize a massive workforce without crippling the food supply. It points to a centralized, administrative intelligence capable of balancing the needs of the stomach with the ambitions of the spirit. This temporal management demanded more than just a feel for the seasons. It required precise tools. They almost certainly used advanced calendrical systems, tracking the solar year with enough accuracy to predict the optimal windows for work. They would have needed to forecast weather patterns, reading the sky and the wind to know when to begin the complex process of moving a 1,000-ton block across miles of open ground. This logistical coordination represents a technology of the mind, a sophisticated organizational framework that was just as vital as any chisel or hammer. The physical movement of the stones was the final, visible act in a long, invisible process of planning and prediction. This holistic system, which integrated celestial cycles, agricultural rhythms, and industrial might, suggests a civilization that saw itself as a part of a larger, living system. Their greatest technological achievement may not have been the stone they moved, but the seamless, sustainable clockwork of society they built to make it possible. A stone was more than a building block, it was a form of ancient currency. Across the Mediterranean and beyond, the quarries of Anatolia produced a material as sharp as a razor and as dark as night, obsidian. This volcanic glass was prized for crafting blades and ceremonial objects, and its journey was astonishing. Blocks of this material were quarried in what is now Turkey, then traded and transported over thousands of miles, reaching communities across the ancient world. This was not an isolated phenomenon. The brilliant white marble quarried from the mountains of Greece became a coveted commodity, its luminous stone traveling by ship to become the pillars of temples and the statues of gods in distant lands. The very existence of these long-distance stone trade routes reveals a profound truth. Quarrying technology was never developed in a vacuum. It was intrinsically linked to a thriving economic engine. The high value of these specific stones created a powerful incentive for innovation. Quarry masters were not just answering to a pharaoh or a king, they were supplying a market. To meet the growing demand, they had to become more efficient. They developed better ways to extract larger, flawless blocks, to shape them into standardized units for easier transport, and to finish their surfaces to a higher quality that would command a premium price. The constant pressure of commerce drove a quiet revolution in stone extraction, pushing the boundaries of what was possible. But this commercial network did more than just move stone, it moved knowledge. A master quarryman from Greece visiting a worksite in Egypt might share a new technique for splitting marble. A trader from Mesopotamia, observing the precise drill holes in Anatolian obsidian, could carry that idea back to his own city's workshops. The stones themselves became the carriers of technological ideas, their very shape and finish broadcasting the methods of their creation to anyone with a skilled eye. This interregional exchange created a dynamic, collaborative environment where advances could cross cultural boundaries and flourish. This commercial dimension adds a crucial layer to our mystery. The missing stage of technology may not have been the secret of a single, isolated culture. It might have been the product of a vast, interconnected economic world, a system fueled by both fierce competition and fruitful collaboration. Rival cities would strive to produce the finest stone, the most impressive monuments, driving innovation ever forward. Yet they also shared techniques through trade, creating a pooled reservoir of knowledge that lifted all participants. This makes the eventual loss of such advanced methods even more poignant. When those intricate trade routes collapsed, whether from climate shifts, political upheaval, or conflict, the dynamic engine of innovation stalled. The constant exchange of ideas ceased. The specialized quarries that supplied the known world fell silent, and the hard-won knowledge they generated, no longer sustained by commerce and connection, slowly faded from memory, leaving behind only the scattered stones as evidence of a once thriving technological marketplace. Sometimes the most telling act was not creation, but deliberate breakage. In certain ancient quarries, we find a puzzling sight: stones that were painstakingly extracted, only to be intentionally shattered or defaced before they could ever leave the site. In Mesoamerican cultures and among Neolithic societies in Europe, quarries were not just workshops, they were sacred landscapes. The act of breaking a perfectly good block of stone was not an act of waste, it was a profound offering. This ritual destruction was a payment to the deities of the earth, a recognition that in taking from the land, a debt was incurred. The stone itself was seen as a living entity, and its extraction required a spiritual negotiation. This reveals a world where human ambition was constantly balanced against a deep reverence for natural forces. Mastery over stone was not a right, it was a privilege granted by the spirits of the mountain. This symbolic dimension fundamentally shaped their technology. The methods they used, the tools they developed, were all filtered through this spiritual lens. A technique that was efficient but disrespectful might have been avoided in favor of a more ceremonially appropriate method, even if it required more effort. The knowledge passed down through generations would have included not just the physical steps of quarrying, but the prayers, the offerings, and the proper state of mind required to perform the work. This adds a profound layer of complexity to the story of lost innovations. When we ask why a certain advanced method might have been abandoned, we must consider that the answer may not be purely practical. A society might have chosen to let a technique fade not because it did not work, but because it violated a core spiritual principle. The loss of technology becomes not just a matter of forgotten blueprints, but a shift in worldview, a decision to prioritize a harmonious relationship with the cosmos over raw, unbridled power. The deliberately broken stones in these quarries are silent sermons, reminding us that for these ancient cultures, the most advanced technology was one that honored the sacredness of the very materials they sought to master. The stone itself became a page. Across the ancient world, quarries produced blocks destined not just for construction, but for communication, their surfaces meticulously prepared to carry the weight of words for millennia. This was a technology of permanence where the choice of stone was as deliberate as the message it would bear. In Egypt, scribes demanded fine-grained limestone or flawless granite, materials whose homogeneous structure could accept the intricate strokes of hieroglyphs without flaking or crumbling over centuries. The quarry master's role was therefore twofold: to extract a block of perfect structural integrity and to ensure its face was a pristine canvas, free of the hidden cracks or crystalline imperfections that could shatter a carefully carved symbol. This required a geological eye capable of reading the stone's story before a single tool ever touched its surface. The preparation process was a science in itself. After the block was rough cut, artisans would begin the laborious task of polishing. Using progressively finer abrasives from coarse sand to powdery silt, they would grind the surface to a flawless, mirror-smooth finish. This was not for mere aesthetics. A perfectly polished plane allowed a chisel to bite cleanly and predictably, ensuring every line of a royal decree or religious text was rendered with absolute clarity. Some research suggests they may have gone a step further, treating certain stones with resins or plant-based sealants to protect the inscribed characters from weathering, a primitive form of conservation that reveals their deep investment in legacy. This fusion of material science and epigraphy represents a cultural pinnacle. The ability to write on such a scale and with such permanence required the seamless integration of multiple disciplines: the geologist in the quarry, the chemist preparing the surface, and the scribe wielding the chisel. It was a holistic system where an advance in polishing technology directly enabled more complex and enduring forms of writing. The decline of this integrated approach had profound consequences. When the specialized knowledge of how to select and prepare the perfect epigraphic stone was lost, so too was the ability to create inscriptions that could withstand the ages with the same resilience. Later cultures often resorted to softer stones or less refined finishing techniques, and their messages, while still powerful, frequently eroded into obscurity far more quickly. The silent, weathered stelae found in later archaeological layers stand in quiet contrast to the crisp, legible hieroglyphs of a perfectly prepared granite obelisk. This suggests that a civilization's voice was only as enduring as its mastery over the very stone on which it was written, a poignant reminder that the loss of a single, practical art can silence an entire chapter of human thought. A stone's journey did not always end with its first use. Centuries after the Great Pyramids rose, many of those same perfectly cut blocks found a second life in new walls and foundations. The Romans, masters of empire, became prolific recyclers of Egypt's stone legacy. They saw the towering obelisks not as sacred monuments to be preserved, but as a ready supply of pre-cut, high-quality granite. They would uproot these giants, transport them across the Mediterranean, and re-erect them in the forums of Rome, often with new inscriptions carved over the original hieroglyphs. This was a deeply pragmatic approach, a testament to practical engineering, but it also reveals a subtle and crucial shift. The Romans were not quarrying and shaping new obelisks of their own on the same colossal scale. They were using the existing, magnificent work of a prior age as their raw material. This reliance on recycling, while economically sensible, carried a hidden cultural cost. The incentive to maintain the most advanced, large-scale quarrying techniques slowly faded. Why invest generations in mastering the extraction of a 1,000-ton block when you can simply repurpose one that already exists? This pragmatic reuse preserved the physical stones, but it did not preserve the intricate knowledge required to create them from scratch. The living tradition of how to identify the perfect seam in the bedrock, how to orchestrate the thermal shock fracture of a 70-ton monolith, or how to achieve that impossible, seamless joint began to atrophy from disuse. The stones themselves became a library of techniques no one could any longer read. This gradual erosion of knowledge is a quiet process, one that happens not through a single catastrophe, but through 1,000 pragmatic decisions. A society that builds its new monuments from the bones of the old may be conserving resources, but it risks losing the very spirit of innovation that made those ancient bones so magnificent in the first place. The recycled stones stand as a paradox. They are both a tribute to ancient genius and a marker of its slow, steady fade from human memory. A sculptor's vision begins not with a chisel, but deep within the earth, where the quest for perfection demanded a quarrying art all its own. For the breathtaking statues of classical Greece, the journey started in the brilliant white marble quarries of Mount Pentelicus. Here, workers were not just extracting building blocks, they were searching for the flawless canvas upon which a master artist would carve a god. The stone for a statue, especially one intended to be seen from all angles, had to be utterly perfect. A single hidden crack, a subtle discoloration, or a rogue crystalline inclusion could shatter under the sculptor's tools or, worse, reveal itself only after years of painstaking labor, ruining the entire work. This demand for aesthetic purity forced a technological leap. Quarry masters developed incredibly refined inspection methods, tapping blocks and listening for the telltale dull thud of a fracture, or studying the stone's grain under the slanting light of dawn to spot the faintest imperfection. The extraction process itself became a more delicate operation. Instead of simply splitting giant slabs, they might have used finer, more controlled tools to gently isolate a perfect block, perhaps employing thin bronze saws and vast quantities of water and abrasive sand to cut it free with minimal shock to the stone. This artistic imperative acted as a powerful engine for innovation, pushing the boundaries of what was possible in the quarry. The loss of this specialized knowledge, however, was devastating. When the great classical periods waned and the priorities of patron societies shifted away from monumental art, the delicate chain of apprenticeship for these refined techniques was broken. The skill of identifying and extracting that one perfect block for a statue was not a simple matter of strength. It was a nuanced art passed from master to apprentice. Once that cultural demand vanished, the knowledge faded with it. This reveals a profound truth about technological progress. The most advanced skills are often the most fragile, deeply entwined with the cultural values that give them purpose. The silent quarries of Pentelicus stand as a testament to a lost synergy, where the human drive for beauty forged a peak of practical ingenuity, a summit that, once abandoned, proved incredibly difficult to ever climb again. Footprints in the dust of an ancient quarry tell a more human story than the stones themselves. Archaeological excavations at sites across the globe have uncovered small, delicate handprints pressed into the clay of pottery used to carry water, the worn remains of children's sandals, and the distinct skeletal markers of women who performed strenuous physical labor. These are not the traces of a society that relegated half its population to the sidelines. Instead, they paint a picture of a community-wide endeavor, where the monumental task of moving mountains was a shared burden and a collective achievement. This social organization becomes a crucial piece of the technological puzzle. When a broader segment of the population is actively involved in the work, the methods that evolve are inherently different. They tend to favor ingenuity over pure brute force, leveraging clever mechanics and organized systems that a diverse group can operate together. Think of the difference between lifting a heavy box alone and moving a piano with a well-coordinated team. The techniques that succeed are those built on cooperation, communication, and a division of labor that plays to varied strengths. a method for moving a colossal block using ropes, levers, and coordinated pulling chants is a technology that can incorporate many hands of different sizes and capacities into a single, powerful engine. This inclusive approach suggests a flexible and adaptive technological tradition, one that drew upon the full spectrum of human expertise available within the community. The knowledge of how to weave the strongest ropes, for instance, or the understanding of which plants yielded the best fibers, might have been a domain where women held specialized, essential knowledge. The preparation of food on a scale to feed thousands of workers, a logistical feat in itself, would have been a critical support technology that enabled the entire operation to continue. Over centuries, however, we see a shift in the archaeological record. Labor patterns often changed, moving toward greater specialization and, in many later societies, the exclusion of certain groups from skilled tasks. As stoneworking became a more exclusive, male-dominated guild, the very nature of the knowledge may have changed. The collaborative techniques that characterized an earlier, more integrated era, the subtle tricks and nuanced understandings held by a wider range of people, could have been gradually sidelined and forgotten. The loss was not just of hands but of perspectives. When you narrow the pool of innovators, you inevitably limit the scope of innovation. The quiet, forgotten contributions of an entire segment of the population may have taken with them a whole suite of collaborative methods, the very social technology that made the impossible seem achievable. The stones did not care who moved them, but the hands that did the work shaped the methods, and when those hands changed, so too did the legacy of what was passed down. Our journey through these 34 clues reveals a startling possibility that ancient quarries are not just abandoned work sites, they are the preserved fingerprints of a forgotten technological age. We have seen the impossible precision of cuts in granite that defy our simplest tools. We have traced the ghostly pathways of stones heavier than 3 jumbo jets moved across impossible distances. Everywhere we look, from the high Andes to the Egyptian desert, the evidence whispers the same story, a story that does not fit neatly into our timeline of slow, steady progress. It points instead to moments of brilliant, concentrated innovation, peaks of engineering genius that were reached and then mysteriously lost. What does this mean for us today? It challenges the very foundation of how we view human history and our own potential. It suggests that our capacity for invention is not a straight, upward line, but a landscape with mountains and valleys, with summits we have forgotten how to climb. This is not about finding lost lasers or alien technology. It is about recognizing that the human mind, when driven by powerful purpose and supported by a unified society, can achieve things that later generations would dismiss as myth. The quiet, enduring stones ask us to reconsider what is possible. They invite us to look at our own modern marvels not as the pinnacle of achievement, but as part of a much longer, more mysterious conversation with innovation. Perhaps by understanding their methods, we can rediscover principles of sustainable engineering, of working in harmony with natural forces rather than simply overpowering them. This exploration is far from over. Each new discovery in these ancient quarries adds